In this lecture, we're going to talk about minimality and cancellations. Now, there are two important theorems that are in this in the chapter material. Theorem 25.2 says a realization is minimal if and only if it is controllable and observable. If and only if it is both controllable and observable. So again, when we looked at realizations, we saw that a system could have an infinite number of state models, and they can even be of different orders. So a realization is minimal if and only if it is both controllable and observable. Now, a system, when you define it from its differential equations, might not be minimal, but that's still the system. So it's important to understand when you have a system that is not controllable and or not observable. But if it is minimal, it is both controllable and observable. All minimal realizations of a given transfer function are similar to one another. So what this is saying is that the transfer function is an invariant in a system. Another invariant is the product of the observability matrix and the controllability matrix. If you were to multiply these two matrices together, so here's the observability matrix, here's the controllability matrix, you will get a bunch of matrices. So for example, H1 is C times B, H2 is equal to C times A times B, and so forth. And we can go through and show these H's are basically C times a power of A. Actually, the index, if we look at the index, the power of that index minus 1 times B. And so we would go through it and we can go show this property. This matrix is a Hankel matrix. A Hankel matrix is a special matrix. In this case, it's a block Hankel matrix because these may be matrices themselves, but they repeat along the anti-diagonals. So this one is repeats, but also it repeats along this diagonal, along these diagonals. So it's a block Hankel matrix, and so those have special properties. Now, another important property is that these matrices, it turns out we can go through and show that this product is written to can be written in new coordinates. So if we transform our system, our ABC matrices of our system, and we form the new observability matrix and the new controllability matrix, that product is equal to the product of the original. So that product is invariant. So basically, if A, B, C, D, and A bar, B bar, C bar, D bar are two minimal realizations, then the product of their observability and controllability matrices is the same. It's invariant. In this case, QC, if it's minimal, QC is onto, it has a right inverse. Likewise, QO bar is 1 to 1. It has a left inverse. And so we can define this product QO pseudo inverse bar, QO bar, and we can go through and show by this equation that that is actually equal to QC pseudo inverse. These matrices will be square and non-singular, even if the system itself is not square. These matrices will be square and non-singular if the system is minimal. So, in terms of cancellations, we can see, for example, if I have a system like this, and it's in series with a system like this, that this S plus 2 is going to cancel with that S plus 1. This S plus 2 is going to cancel with that S plus 2. S plus 1 is going to cancel with that S plus 1. And we can go through and show that we get this transfer function. So 3 times 3 divided by S plus 7, S plus 5. So this combination is not minimal because we should have 4 poles, but we only have 2 poles. Okay, so there is something to that. So in looking at all of this, we're going to look at these 3 sets of interconnections: series interconnections, parallel interconnections, and feedback interconnections. So this we're going to look at in the next video. These 2 we'll look at the video after that. So it's important to understand when we are talking about interconnected systems and minimality. So again, we would be looking at things like uncontrollability. So a system is uncontrollable. So AB is an uncontrollable pair if there is a non-zero W such that is an left eigenvector of A such that WB is equal to 0. Likewise, the system is unobservable if we have a right eigenvector such that that eigenvector times C is equal to 0. And again, we have invariant zeros if for some value of lambda, if there is some x and u multiplying that is in the null space of this matrix. Okay, so that's going to be important to look at when we examine the controllability of series interconnections and so forth.